All right. Good morning, everyone. Let's start. Do you have any questions about anything? All right, so let's kind of finish discussing some introduction ideas to regression. So last time, we were discussing the idea of linear regression. And to emphasize, the model that we're using, the actual title in the textbook, they call it normal linear regression. But I mean, usually when you say linear regression, the assumption is that you're discussing the normal linear regression model anyway. So first, right, the model or the assumption is that you have yi that are normal with mean a plus bxi, variance sigma square, and they are independent. So here, a and b are unknown parameters. So actually a, b, and sigma squared, right? The xi are known, all right? And it's better if we think of them as constants for now, right? They're just data. They're just part of the data. I mean, to be fair, right? The y are also data. I mean, the y is not like we'd also see the y, except that it's always good, right? Actually, it's important to remember that in this context, when I mean constants, I really mean deterministic, right? The yi's are the random variables, while the xi are just deterministics in this context. And so we discussed, right, the approach here, or the MLE approach. So we do the MLE approach, and we observe how the A hat, B hat, MLE give the same answers, right, as the same as when you try to minimize the yi minus a plus bxi squared. The reason, right, is because this term right here are exactly the term that shows up in the exponential, right, of the normal distribution. So when you maximize the MLE, the likelihood, exactly you minimize this term, which, right, from the context of least square, you're minimizing the distance between the line, the straight line, and the y, right? So then we actually solve this equation and get b hat, right, to be sxx or sxy over sxx, a hat to be y bar minus b hat x bar, and then sigma hat squared to be RSS divided by n, where our notation is sxx, right, is the sum of xi minus x bar squared. Sxy is sum of xi minus x bar, yi minus y bar. It's the covariation. And you can have SYY in here too, which we don't use. And RSS is the residual sum of squares, which is sum of yi minus a hat plus b hat xi squared. Okay. So these are the MLE estimator that we'll get after we solve for this equation. All right. So that was the that was kind of like my goal, right, is to show you how the regression framework is just sort of everything we did throughout the semester put together. So first you pose the model, then you solve for the estimators, right? And then you ask about properties of the estimators, including sampling distribution, right? And actually sampling distributions will give us the other properties such as biasness, right? Or confidence intervals, that kind of stuff. But I guess before that, let us just take a look at typical linear regression output from a program, right? Which I think you have seen somewhere before as well, but might as well just kind of put it into a context. All right, so like this, so here I have a sample of 20 points. I put my true intercept to be 1, my true slope to be 2. My standard deviation is 4, okay? So my variance is 16. My true variance, right, is 16 sigma square, right? Okay, so I generate x equally spaced between 0 and 10. Here I follow a slightly different approach, but I'll tell you, it's the same thing. But basically, to generate the y, okay, I view y as the random fluctuation from x, the perturbation of x, okay? So y is going to be a perturbation of sorry, not from x, from the straight line, right? From the straight line, a plus bx, okay? With, you see here, sigma times e is the noise, with the noise of standard normal. So if I multiply by e, right, by sigma, right, I generate the normal 0 sigma square. So that's my perturbation, okay, from the straight line. Anyway, right, this is just a slightly different way to view it. And then I run the regression, output things. And here's a typical output that you'll see, right, from a regression result. Again, if you have done anything like R, whatever, you have seen something like this. The point is, right, actually, that I always feel when you look at this table, you probably feel overwhelmed at first. There are a bunch of output, right? But some of these things, for example, you see, this is the A hat, this is the B hat, right? This is the standard deviation estimator of the A hat, standard deviation estimator of the B hat. P-value, the P-value we talked about, okay? The T-stat, the test stat, okay? So there's some hypothesis testing attached with this, right? There's a confidence interval, right? This is, I guess, 0.05, right? Confidence interval. Anyway, right, we'll talk about this. But you see, like, hypothesis testing and confidence interval are baked into this kind of result, standard output, but we'll talk about that. Anyway, right, let's just look at the output. So for this particular one, you see, of course, the true constant is 1, the true slope is 2, as I showed you. The estimator, right, of the constant estimator is 2, pretty far away, right? The slope does a better job, 2.2. The noise is even better, right? This is the sigma square estimator, 16 versus 16.4. And you see here is the true line, right? The line of the true relationship of the mean, right? Again, notice, right? Y itself and X definitely does not have any true linear relationship, right? Because Y is a perturbation of away from this, black line, right? Oh, I'm sorry. Black line is linear regression, sorry, this line, right? The true relationship is here, right? Anyway, Y is a perturbation from this, but the regression line, right, is not far away from this. And every time you run, right, this, I guess every time you resample, right, keeping the same, by the way, right, so this is the relationship of the mean, right? The mean of Y follow a linear relationship with X, right? Y itself is a perturbation from that. If you run that again, you get a slightly different thing, right? So here, notice the constant for some reason, right? The constant term is not doing very well here, right? And this is That's why probably they look parallel, right? Let's look at one last time. Here, yeah, also the constant term doesn't seem to be doing that well. But you see, the point is this, I find it a little bit interesting that, right, from our point of view, if you just look at term by term, that doesn't seem to be doing spectacularly well. But when you plot it, right, these two lines look really close to each other. So, I guess, again, right, regression overall is try to balance all these errors, right, not just one single one. So a constant term move like that doesn't really affect that much. Notice how the regression estimator also is doing not very well here, right? Of course, right, it goes without saying that if you increase the data, right, if you make it into, I don't know, I'm not sure, depends on how many I can push here. I'm not sure 100 I can push, but let's say you have a 100 data point, right? You see that then the estimator becomes really, really precise, right? And then the more data you have, right, the more you can capture that true linear relationship between the mean of y and the x. Okay. And we'll talk about the data output soon after this. But do remember, right? I guess the point is this, that the computer right nowadays can already do all these calculations for you. So, right, calculation is not the point. The point is how to interpret, right, this data, how to know how to read this table, right, comfortably. And again, you see, p-value is a standard output in here, right? You don't see a rejection region, you see a p-value, for example. Question? So maybe let me talk about the other formulation. Whoops, what am I doing here? The other formulation real quick, which is very simple anyway, but is helpful to look at. Another framework for linear regression. So the other framework you might see is this, that you see yi is equal to a plus bxi plus epsilon I, where epsilon I are IID, normal, 0, sigma square. Okay, so that is the other way that people usually phrase it. And to be fair, I think this is probably the one you see more often than what I wrote up here. Okay. Or maybe I don't know, in a machine learning class, you may see this. In a statistics class, you may see this. Right. But so actually, there's something to be said about this as well, the relation between these two. Right. First of all, I mean, I guess it feels comfortable to be able to write IID back, right? Again, this is really true because, right, the noise are IID, right, with mean 0 and variance sigma squared. So from this point of view, right, this is constant, this is random. So yi is a perturbation, right, away from this trend, right? This is this linear trend. So same thing, right? A, B, sigma square unknown, xi are the observed data, yi are the response. But so let's probably ask a kind of a redundant question, but still, right? So for example, in this context, we have the IID, right, sample like this, which is, right, really good. Notice how, right, here we have to use, let's just say, residual sum of square, right, to estimate the sigma square term, for example. And this is a bias estimate anyway, okay? We'll talk about that. But why don't we use this formulation and say something like this, right? Sigma hash square is going to be sum of epsilon I square divided by, I don't know, let's say n minus 1. right? Like, isn't this formulation much easier than the other one? Why do we have to, phrase everything in terms of A hat, B hat, and then define residual squares, that kind of thing? We have the epsilon I here, right? IID data. What? Why don't we just go ahead and do that, for example? You understand the question? Or maybe it's too silly. So in other words, right, it seems like in this framework, I just do regular statistics, right? And this seems pretty straightforward for me to estimate some parameter like sigma square, for example, like this. Why do I have to bother rephrasing it in some kind of complicated normal distribution like this? So the point is this, okay, that this is really a silly question, because when you write something like this, it's nonsense, because epsilon I are not observed. Okay. And again, I guess it's pretty simple. When you look at a model, you should kind of know this. But I do believe that, mistakes like this tend to slip in here and there, and it kind of mess around with your understanding. That, the whole point of posing this model like this is that, again, right, I kept emphasizing known and unknown parameters, but same goes with, observed and unobserved stuff in real life experiment, right? So epsilon I, even though it's some sort of random variable that plays a role in your data, you don't get to observe the noise, okay? You get to observe the output, the yi. So whether you pose it like this or pose it like this, right? It doesn't really make a difference. It just makes you more comfortable to view the model. But the epsilon I, you cannot use directly anyway, okay? So that's just an unobserved noise. You observe yi and xi. So therefore, right, the formulation of the direction, the distribution of yi directly is what you use, right? This is good. I mean, for kind of like understanding how the y reacts to the x with the noise, but when you have to do statistics work, right, you have to do it on the y because the y are the observed data. Okay. So, questions? All right, so let's go to the sampling distribution. So first, right, so the sampling distributions means we want to know how B hat, A hat, and this guy, right, are distributed, or really the focuses of the RSS. So notice that, right, first of all, so here, right, the emphasis is you must know where the randomness comes from. So the randomness, right, comes from the y. That's why we put y as a capital letter. So here, for example, you see that in terms of B hat, right, SXY is like this. So this is normal, this is normal. So it's some kind of sum of normal distribution, okay? So the y's have the joint normal distribution. So that means that B hat has some normal distribution because it's a linear combination of normal, okay? So of course we have to fill that in. But the observation is a combination of normal, right? Linear combination of normal, so it's normal. Same goes with A hat. Y bar is normal. B hat, right, is normal from what we said before. X bar is just a constant. So combination of normals, right, is normal again. Now, as you will see, these formulations are not optimal. I mean, they are actually quite intuitive to remember, but in terms of sampling distribution, if we care for sampling distribution, formulating them in this formula is not the best way to do work. Okay, and we'll see. But anyway, right? Last time we showed that expectation of B hat is B, and expectation of A hat is A. All right. So these are unbiased estimators. So we can go ahead and fill in B and A here. Okay. All right. So how does that work? Let's just see the calculation again. Expectation of B hat is expectation of SXY over SXX. And that will be 1 over SXX because X is constant, sum, right, of XI minus X bar, and the expectation only hits on the Y, like that, okay? And so you get 1 over SXX, sum of XI minus X bar. YI, of course, has expectation A plus BXI. Y bar has expectation A plus BX bar. So when you cancel, right, and you factor this out, that's exactly SXX. The only term left is B. What about A hat? Expectation of A hat, right, is expectation of Y bar. I guess let's put it in capital Y, minus B hat X bar. Whoops, X bar lowercase because it's deterministic, which is expectation of Y bar minus expectation of B hat, right, X bar. So again, you see, being able to distinguish what's random and what's not is the first thing we need, right, to be able to work on this. If you look at this term and you don't know what's random, what's not, and you try to calculate expectation of X bar, you're just going to waste 10 minutes, right, of your calculation, not doing anything useful. So, all right, so Y bar, we have said is A plus BX bar. And B hat, we already said is B, right, above, so clearly it's A. All right. Any question? Okay. So the next thing, of course, is to address the variance, right, of these terms. These right here, by the way, are exactly that, or not quite yet, but this is the standard deviation entry in the output of the regression I showed you before, right next to the constant coefficient, right next to the estimator of the coefficient, then you have the estimator for the standard deviation. That's kind of this guy, right? Not quite, but we'll see. Okay, so variance of B hat. How will we do this? Well, so let's just plug in, right, the definition, not the definition, the formula, SXX over SXY over SXX. Now, SXX, right, just factor out as XX squared. That's easy because it's constant. But the XXY term, we have to look at a little bit because this is going to be XI minus X bar, YI minus Y bar, right? So let me ask you this. Can I pass in like this? This is a constant, so it just goes out as a squared, and then variance of YI minus Y bar. Can I do that? And then, of course, right, I will handle how that, combine by some technique, but can I do this? The answer is no. No, not that, right? I already took care of it. This is a constant, right? So when you pass it out of the variance, all you have to do is square it. So that part is fine, right? So xi minus x bar is a constant, right? It's deterministic rather. So, right, it can just be factored out of the variance term. That's fine. That's not the issue. The issue, right, is that the yi minus y bar, these terms right here are not independent, right? You have this variance of a sum being the sum of the variances. That's what you're saying here. Only when the terms are independent. If the terms are not independent, you have to add covariance. Okay? So here, because every term here has y bar, they're not independent. Okay? So if you want, right, you have to add the covariance terms of these guys, right, of the sum. So that's not correct. Okay? Now, I guess same goes for a hat, maybe. Variance of a hat, right, is variance of y bar minus b hat x bar, question mark, variance of y bar minus x bar squared, variance of b hat. So one thing that's kind of interesting is you see somehow, right, the a hat, right, the estimate of a hat depends on b hat. Therefore, if you know everything about b hat, just like you know b hat is unbiased here, the calculation of a hat just kind of piggyback on that. Same thing here, right? If you know the variance of b hat, which we did not do, right? But if you know it, then you can just plug that back, just plug that in here, right? Variance of y bar is actually easy. Right? What is variance of y bar, for example? So what I was saying is this calculation is wrong. Does that make sense? This calculation is wrong. If I want to continue it this way, I'll show you the right way to do it. But if you want to continue, in spirit, you have to do something like this. Do you understand? And I refuse to look at this formulation right now because it's not something convenient or even necessary to work with. But if you want to push this line of calculation further, you are required to include that. Is that okay? Because this term right here is non-zero. Or it could be zero, who knows, but at least you have to consider that. Yeah. So what I'm saying is, right, that again, this doesn't happen so much under the so-called quote simple statistics we've been doing so far, right? I know it's not simple to you, but you see in view of something like this, right? The things we did before is indeed simple, in the sense that the relationships between stuff are always independent, so you can blissfully forget, right, all the other stuff. You just kind of do variance calculation easily. Here, right, the dependent structure you have to really be mindful of. I think it turns out that this is zero anyway, right? But I'll have a better way to do it. So same thing here, right? Does this work like this? Can I pass the variance in like this? Can I pass the variance term in like this? Yeah, right. Correct. You have to consider the correct. You have to consider the covariance between y bar and b hat. ironically, all right, ironically, is actually equal to 0. We can show it's equal to 0. So if someone blissfully do this and get the result, they are accidentally correct. Okay, but I emphasize that being accidentally correct is nothing to be proud of, because you may make the mistake again in the future, right? And in fact, it's probably by pure luck or some weird connection that this is 0, right? It is true, but I highly, right, not actually, I do not push this yet, right? You cannot push this calculation like this, right? You have to consider this term. So anyway, right, I would just tell you that in the whole point I want to make is this: A hat and B hat, right, in this formulation are highly intuitive, all right, highly intuitive. I think every one of us can understand what A hat and B hat is doing here, except that in terms of calculation, they're not super convenient. So for this purpose, right, you will see in, again, more advanced study, right, there's this intuitive formulation, and there's the more technical formulation that is more conducive to calculation. Okay, so a reformulation or let me just do this, a reformulation of A hat B hat. All right, and again, the purpose here is to review their distribution nature in an easier way for us to study, right, their sampling distribution. And it's like this. Actually, it's quite simple. B hat now will be sum of xi minus x bar times y bar 1 over sxx. And A hat will be, so A hat is a little bit more painful. Oh, sorry, not y bar, yi. A hat will be sum of sxx plus nx bar minus nx bar xy xi divided by n sxx times yi. So for that purpose, actually, I can just put one of this over sxx in here. Okay, so this is going to be the formulation that we will use to work with B hat A hat. So, right, we'll talk about why this works. So basically, we say that from the other formula, we can rewrite them like this. This indeed is one of the problem in the text, okay? But let me ask, right? First of all, when you study these things, working out the formula is one thing. That's actually the less important stuff. The more important stuff is to ask why. Why is it that we want to look at them like this? What is the advantage of this formulation versus, you know, again, right? Sorry, where is it? Here, right? Versus this. This is very intuitive. I would say that no one can make head or tail out of this. But why? Why is this conducive to distribution study? And that's important, right, for you to understand the reason for the work that we do. This is good simply because they reformulate A hat, B hat as linear combination of yi's. Okay, so in other words, basically they write something like this. well, some others see. But at the heart of it is just that, where, of course, the most important thing is these guys are constants. These guys are deterministics. So look past, right? Look past the ugliness here a little bit. Of course, we have to deal with them if we want concrete result. But past the ugliness, it's just a linear combination of the y's. Why are they beautiful? If you want to study distribution, they're beautiful because the y's are independent. So then you know everything about A hat, B hat in this structure, right? Ignoring what the CIR actually is. But if you know this, then really the A hat will have, right? If in this formulation, the A hat will have, so suppose the yi, right, are normal with mean mu I and variance sigma square. That's what happened, right? IID, not IID, they're independent. Then the A hat will be normal with mean sum of Ci mu I, and with variance sum of Ci square sigma square. Same for B hat. You understand? So splitting it like this puts all the random action on the y's, and they're independent. Notice, right, the number one reason I complain about this formulation is that these guys potentially harbor some dependent structure that I'm not aware of. Okay, well, here they're not. There's nothing dependent between the terms. And in fact, there's even a deeper message here. That is, in linear regression, at least in normal linear regression, the coefficient estimators are just linear combination of the response. Okay, that's more important. And this is a true fact in general, as hopefully I'll tell you at the end of this session, that the coefficient estimators are just linear combination of the response. And of course, right, the coefficients in the linear coefficient, the linear coefficient are made up from the x data. But the guy, right, is the y, right? The linear combination of the randomness is the y. So that's it, right? This is a more informative structure to use when you want to study the variance and stuff like that. Question? Okay, so why is this true, for example? All right, you may want to ask. So before, right, I have B hat to be is sum, right, of B hat is SXY over SXX, which is sum of XI minus X bar, YI minus Y bar, divided by SXX. Now you tell me that, well, you know what? B hat is just this. So you're telling me that these are the same. Why is that true? Right? And the same thing for A hat, right, which we'll address later. But let's just look at this. Because again, right, my experience tells me that even this small step can confuse a lot of students, right? But if you're experienced and you know where to look, you'll see that this is immediate. You see why they're the same? Clearly, they're the same because this term is 0. Okay, and you'll be like, what in the world, right? How can this term be 0? Well, why is it 0? The reason is, right, and this is an important trick, when you consider the sum, right, this is a sum over I. The y bar, right, does not depend on I. So really, it's just y bar times the sum. But then do remember, right, that summing xi and the sum over x bar is the same. Because, right, that's exactly what x bar means. Right, x bar is the average of this guy. So when you sum them back up, they're the same. So that's why it's 0. Is that okay? So that's why basically in this formulation, even though it's very intuitive, right, for regression. Why? Because it tells you about the fluctuation of y, right, and x together, normalized by the fluctuation, the variation of x. Well, in terms of calculation of distribution, this term is totally redundant. You don't need that, right? It just introduce some maybe unnecessary dependence, some artificial dependence that you don't need, right? In terms of calculation, you much rather work with this. Okay. Question. What about the a hat? So the a hat, right? By the way, this is a homework problem from the text, but let's take a look, right? Y a hat is y bar minus what was it? B hat, right? X bar. Okay. Now, what do we want to do? We want to somehow reduce this to just dependence on yi. All right. Just remember the goal of the calculation, and then you'll be able to do it. The goal is somehow to reduce everything to yi, to dependence on yi. So obviously, right, we have to somehow untangle this and then just say that it's yi. Well, the y bar is easy. It's 1 over nyi. B hat, well, right there. So what does that mean? Well, you can just factor. Okay. And I won't do some kind of simplification work unnecessarily, but you will see that, right? The textbook write that eventually they want this. I don't know. I don't care for that so much, but you see, it's going to be sxx plus nx bar square minus nx bar xi. And I hope, right, you see that this step to this step is just a common denominator, right? You see, that's the common denominator. This term goes here, this term goes here with some, you know, cancellation, right? Sorry, I missed one thing, right? Because this is b hat x bar. So b hat x bar, so I missed an x bar here, sorry. So I missed an x bar here. So yeah, all right. X bar times this. So yeah, okay, that's why you have the nx bar square and then x bar xi. Question. Okay, so remember, why do we drag in all these things? Because we want to know the sampling distribution of a hat, b hat. Okay, so notice that we easily calculate the mean to be a and that they are unbiased, but we want to decide their variance, right? And I hope you remember that in all of our work before, right, calculating the variance of an estimator is much more tedious, right, than calculating the mean. Same thing here, right? But anyway, now we have this, right? Let's just do it. So variance of B hat will be variance of, now using our new formulation, which is sum of xi minus x bar divided by sxx, right? Times yi. Well, what is it? These guys are independent now, so I can just pass everything in, which is sum of, right, xi minus x bar squared, variance of yi, and I can do 1 over sxx squared. Oh yeah, okay. So starting with this, right? Again, the point is to express everything in terms of yi. All right, you want to express everything in terms of yi. So you unfold this expression in terms of yi. Y bar is like this, right? Definition. B hat in terms of yi is this, and that's exactly our work in the previous ones, right? And after you get this, then it's a simple factorization, right? Factor out of yi is sum inside. And then the textbook gives you this formulation, but you see it's simply a common denominator. Is that okay? Sure. Again, tedious calculation that really doesn't mean much here in a way. All right. All I want to show you is the spirit of the calculation. You can redo it yourself, right? The concrete results are not important. The idea is important. Okay. So anyway, down to here, right, where I use the square on this, do this. Now the yi have the same variance, so that's just sigma squared. Okay. And what do we call this again? What is this? This is sxx. Yep. So you see that finally it simplifies to something very simple. So what we conclude then, right, is B hat is going to be a normal with mean B and variance sigma square over sxx. So I won't do the work for A, okay, A hat, but A hat will be normal with mean A and variance sxx plus n x bar squared times sigma squared divided by n sxx. Okay. So how do you get this term? Well, I guess you kind of understand it by now. Just take the variance of this. Just take the variance of this. Or actually here, I would say that taking the variance of this is actually painful. Kind of going back against my word here, this calculation actually will be simpler a little bit, as long as you can prove this, which is not that tough. All right. So actually, I would go against my word a little bit in terms of taste, because taking the variance of this means you have to square this term, which 3 terms like this is just a little bit messy. Okay, this is a little bit cleaner anyway. But this is really the true meaningful formulation, all right, for A hat B hat, because they do express the idea that the estimator is a constant, is a linear combination of the y's. That's important, right? So next, let's talk about the RSS. RSS, which is sum of yi minus a hat plus b hat xi squared. So this should remind you of sum of xi minus x bar square, right? Remember the good old day when things are simple? Or rather, right? I mean, yeah, let me just do this. But do remember, right? In this context, the xi are normal, okay? This is not constant. The xi are normal would mean mu invariant sigma square. All I'm saying is this is also RSS, right? This is also RSS. This is a residual sum of square with a, you know, when we only regress on the constant, right? No slope. So anyway, right? The point is this is a chi-square, right? Remember that we have the result that n minus 1 s squared, right, over sigma square, which is going to be a chi-square n minus 1 distribution. Okay, or really, right, in this formulation, if I call this RSS, okay, then n minus 1 RSS, right, has a chi-square n minus 1 distribution. Whoops, what am I saying? RSS over sigma square. I apologize. Because you multiply by n minus 1, you get back to RSS, right? RSS divided by n minus 1 is s squared. So it should not surprise you that in this context, all right, I'm not sure if I'm confusing you by using the same RSS. Let me just call this RSSX. Okay. This is basically reminding you of the old problem, the normal problem, right? Then this is what we have. Just introducing the new term RSS, but you know, this is just that term that we had before. Here, let's call it RSSY. Then it should not surprise you that I have this RSSY divided by sigma square has a chi-square n minus 2 distribution. Okay. Why? So first, why the 2? Right? That's all I want to say for now. Why the 2? 2, remember, right? I explained before, why do we lose 1 degree of freedom here? We lose 1 degree of freedom because you have to estimate x bar. You remember, right, in your quiz, right, of last week and this week, if we have the mu here, if mu is known, if you don't have to estimate the mu, then this becomes chi-square n. Okay, you lose no degree of freedom to estimate the variance. But if you have to estimate x bar, then you lose 1 freedom. But now, of course, if you have to use 2 degrees of freedom to estimate the mean, then you lose 2 degrees of freedom. Okay, so in general, in a regression problem, in a normal regression problem, with p, okay, coefficients. So, or with p covariates, I think that's what they say, right? With p covariates. No, p minus 1 because constant doesn't count as. I'm not sure you call constant as covariates or not. Maybe let me just say p coefficients. So this is counting constant. Counting the intercept. Then you have RSS divided by sigma square will be a chi-square n minus p distribution. Okay, so you lose p degrees of freedom to estimate these p coefficients for the mean. You know, like so there will be C0, C1, C2, C3 up to Cp minus 1 to calculate the mean. All right. So that's the principle. You ask, why is it chi-square in this case? And I answer, I don't know. I mean, I do know. I just don't know how to explain it to you using this formulation. The reason is this is going to be super messy to untangle this. And I don't know how to untangle this in this formulation. The right way to approach this is through matrix notation, okay? Which I'll try to show you a little bit at the end of the class. But if I really want to show this as a chi-square distribution, the only way I know is through matrix notation, okay? But so accept this for now, that the residual sum of square, okay, that's a more important concept. Normalized with sigma square will be a chi-square distribution with appropriate degree of freedom. Degree of freedom is just the data point minus degrees of freedom loss. Okay? Question. So, right, you see this, that basically a very popular estimate of sigma square, right, will be RSS divided by n, right? We see this all the time, and actually this should be at sigma hat MLE. I think it's always like this. You see, is always biased, right? Unless p equal to 0. Unless you know everything, unless you know the mean itself, then you don't have to estimate anything, right? Even when p equals to 1, which is the case when we only use the intercept, right? The classical case that we talked about in this class, this is still biased, right? And of course, the more coefficients you use, the more biased it becomes. So this, even though it can be used as an estimator, right? And actually it does come out from the MLE estimator, this will be always a biased one. So the unbiased estimator, right? It depends on what notation you use. But I'll stick to the S square. S square will be RSS divided by n minus p in general. Is that okay? Any question? All right. So we are done in terms of looking at the sampling distribution of A hat, B hat, and even, you know, S square, right, or sigma hat square, if you will. So in the scheme of things, we're done with kind of chapter 10 in the textbook, right, from before. What's the next question we ask? So after we have the estimator, after we know the sampling distribution, what's the next question that we ask? So the purpose of RSS, right, doesn't matter Y or X, whatever. I just kind of separate them because I don't want to confuse you between these two cases. But basically, this is the regression when you only run regression on the intercept. This is a regression when you run regression on two coefficients, right? And in general, you can run regression on p coefficient like this. Cp minus 1. Of course, we C hat. Okay. So again, first of all, conceptually is always whatever remaining error you make after you do your estimate. The purpose, right? The very purpose is exactly this divided by the appropriate normalizing factor will be an estimator for the sigma square. So the general model, right, will be yi, or not too general, but this is going to be yi is going to be some normal, C0 plus some I from 1 to p minus 1 of CI sigma square. That's the model. So the question is, how do you estimate C0, C1 to Cp minus 1? And then, right, you have to estimate sigma square. So the purpose of the residual sum of squares is exactly the term you use to estimate sigma square. Something like this, or actually something like this, is called a mean square error, right? The MSE. You hear MSE of the model. Mean square error of the model is exactly this term. Is that okay? Okay, so back to my question, right? After you get the sampling distribution, whoops, here, right? So after you get the sampling distribution, what do you do next? What's the next question in statistics after you get the estimator? Absolutely, right? Confidence intervals and hypothesis testing, right? Now you can do these concepts for A hat, B hat, and sigma square, right? Because they're all estimators, you can apply this to all of them. Traditionally, right, people don't do it for the intercept. So usually people don't do confidence interval and people do them, but hypothesis testing. The reason is, like your data can be shifted by a constant, right? Your response can be shifted by a constant, and it will change your constant estimator. So it doesn't mean much. The slope, right? The non-intercept terms is much more important and much more relevant just from the interpretation point of view, right? To do estimators. To do hypothesis testing and confidence intervals on. So sigma square also can be done, but that's a side issue, right? So I'll focus here only on showing you B hat. Okay, so B hat, right, is normal with mean B and variance sigma square over SXX. Okay, so what's going to be the confidence interval for B hat? One minus alpha confidence interval. So if you kind of remember what we did before, right, you can easily guess something like this. Oh, sorry. So confidence interval for what, right? I have to say confidence interval for B, right? It will be B hat plus minus T n minus 2 alpha over 2 S divided by square root of SXX. Is that okay? And you see, like, it's quite intuitive, right? Why do I know this? Because you must start at B hat. Why the T? Because I have to estimate the sigma square. Why n minus 2? Because I lose T degree of freedom, 2 degrees of freedom. Alpha over 2 is confidence level. The S standing for sigma, square root because I do standard deviation, right? Notice in the textbook, on page 396, okay? They will have some square root term like this. And then they have sigma hat instead of my S. You know why the textbook has this term and I don't? That's because the textbook used the bias estimator. They use by sigma hat here, they use this term. They use the MLE estimator. So they have to balance it back for the confidence interval. I use S, so I don't have to normalize it. Okay, so I think this is much cleaner. And again, right, please kind of try to see that this is very intuitive. That you start from the B hat, you just run with the standard deviation spread, and then the measure is Tn minus 2. If you really want to, right, rigorously show this, what do? You have to show that B hat minus B divided by S over square root of SXX has Tn minus 2 distribution, which I don't think is super hard to show, right? Assuming all the knowledge we talked about before. Question? In terms of hypothesis testing, right, what do we test? The most common test, and actually I think the test, is B equal to 0 versus B non-zero. Is the most natural test to be done in this context. Why? Because B equal to 0, right? If B is truly 0, what does that mean? That means Yi is normal A sigma square. That means there's no linear relationship between Y and X, right? No, no relationship between Y and X. So if, Y is your response, right? And X is some kind of control variable. Like, I don't know, testing vaccine, effectiveness or something, right? Then if there's no relationship between the vaccine and the response, that means your vaccine is ineffective, right? So that's why you really care for this. If there's no relationship, that means whatever you're trying to establish there doesn't hold. And of course here, right, there's some relationship. You don't care if it goes negative or positive, right? You just care that there is some significant relationship between X and Y. So Y and X indeed follow some relationship. So anyway, right, but from our point of view, it's pretty easy because what is our test stat? Right here, with B equal to 0. So you would reject when absolute value of B hat divided by S divided by square root of SXX is bigger than Tn minus 2 alpha over 2. Do you see how, right? The point I want to make is if you are fluent in the context of hypothesis testing, and confidence intervals, it's exactly the same knowledge that get translated here, just in a different model, but same concept, right? Also, what's your p-value? P-value would be probability of Tn minus 2 bigger than absolute value of B hat. And that's exactly the p-value that the computer program output for us. Question? All right. So what I want to say is this, right? That It's not super important that you follow all the technical details here, but I hope you see how everything we covered in this class carefully in terms of concepts gets applied in a typical regression problem. And from here on, right, the sky's a limit in the sense of what? In the sense of your models can get more and more complicated, right? You can add more and more variables. You can do your regression in more complex way. You can, penalize regression, etc. Then the technical details get super much more complicated, right? I mean, I cannot even track some of them. But at the foundation of it, the questions are still the same. The hypothesis testing, the estimators, right? I guarantee you that the concepts are still the same. So if you get lost, you go back to the foundation and you trace it back. Hopefully you be able to kind of follow the thread of the conversation, right? And again, right, if I can give you any advice, don't lose track in the technical details. Formulas are not scary, okay? They should tell you some story. So if you can track the concepts, you should be able to untangle what the formula is telling you. All right. Questions? Okay. So for the last 10 minutes or so, I just want to tell you something really quick about what's next. I mean, what's next, not in this class, but you can pursue in other classes or some you may have seen before. What's next is, the appropriate way to discuss this kind of problem is the multivariate setup. Okay, where you have y vector is going to be a normal with x beta sigma square I, like this. So X is a matrix of 1, and then X1 all the way to, let's say, X1 P minus 1, sorry, XP minus 1, 1. Beta will be beta 0, beta 1, up to beta P minus 1. I mean, I guess people go with P anyway, so they're like, So, all right, so X is going to be an N by P matrix. All right. Beta is going to be a P by 1, right, vector. So like that. So in this framework, right, what you need to understand or what you need to learn is something called the multivariate normal distribution. And you will probably spend a good, at least one week or one lecture to study all the properties of this. But let me tell you real quick, okay, how things work in this setup. And it's very beautiful like this. So the way you work is something like this. You try to solve for y equals to x times beta, basically. Okay, forget the error term. But of course, exactly you cannot solve this because there's an error term of y is not exactly equal to x beta. So what you do is you multiply both sides by x transpose. And it turns out that if the columns of x are linearly independent, then you can this guy is invertible. And so you get beta hat is x transpose x inverse x transpose y. Okay. Then there is one more result that I will say is this. In multivariate statistics, right? A very simple results like this. If variance of y is sigma, so this is going to be an n by n matrix. It's called n by n covariance matrix. Then variance of a times y is A sigma A transpose. Okay. Applying that to this context, what we have is variance of beta hat is X transpose X inverse X transpose sigma square IN X transpose X inverse. Because the transpose of this, right? The transpose of this is just like that. And you see the identity cancel, sigma square is a scalar. This it simplifies down to sigma square X transpose X inverse. Remember how much work we have to do to get to the variance of A hat B hat? It's just this. It's just simply like this. Let me show you, right? When we have P equals to 1, right? That means we only have 1 and X. Okay, so 1 is the vector of 1s. Then X transpose X will be what? 1 transpose X transpose. So X is the vector of, X data times 1 and X. What is it? 1 transpose times 1 is N. 1 transpose times X is sum of Xi. X transpose times 1 is sum of Xi. X transpose times X is something we call sum of Xi squared. Okay. Which, if you factor out the N, you'll become 1 X bar sum of Xi squared over N. How do you invert this matrix? Well, you have to calculate determinant, right? Determinant of the inside matrix will be sum of Xi squared over N minus X bar squared. You know what this is? This is N times SXX, because that's exactly the variance. So therefore, X prime X inverse will be, right? Oh, sorry. It will be SXX over N. So X prime X inverse will be N over SXX, 1 over determinant. You also have to flip this. So times 1 over N. You switch this, and you negate that. Which is 1 over SXX. Oh, sorry, sigma square, right? So yeah, that's fine. So sigma square times this will be sigma square times this. How do you read this? This will be the covariance matrix of A hat B hat. So this term right here is variance of A hat. This right here is variance of B hat, and you see that's exactly what we got. You got a bonus. You got the covariance term. So these guys are the covariance terms like this. Okay. And so you see, I hope it's not too scary, but the calculation done here is much more convenient than the calculation I've done up there. And in general, if you increase the level of variables, right, if you have like P columns like this, forget writing them down in terms of specific entries. All you got is this, and that's fine, right? Because you can ask the computer to calculate this out for you. Okay, but so again, right, this is not something this class covers, right? This is going to be on a more advanced class where you're going to deal with like multivariate stuff. But this is the appropriate home for it, right? Not here. So here I did this. That's why I say don't worry about technical details. I want to show you that the ideas, the statistical ideas that we did applied. So what's next is you will learn the multivariate setup, and you will learn how to apply the ideas we talked about in this class in the multivariate setup. Okay, and hopefully some of you will get to see that in some other courses. All right, so that's the end of the course. Thank you for joining. In terms of the exam, right? So in the following two Wednesday, the next Wednesday, it'll be cumulative. All right. Probably materials will be kind of equally spread out through all the sections, all the materials. I will post the old exams soon so that you can take a look, you know, if you want some, but there's no guarantee that my next exam will be like that. No quiz, no more homework due, right? This is it. But I will still post, you know, some homework and some quizzes. They're not due, but they're relevant, okay, for the final. You will get double your cheat sheet, all right? So instead of one, you can use two, all right? You can reuse the old ones if you want, or you can make new ones, but double, okay? In terms of curve, all right, I'll say this, so in case someone you ask, the curve will be slightly higher than what I told you in the midterms because you get to factor in the quiz and the homework. But I aim to make the passing grade. Yeah, I'll ask the TA to hold review for you. Oh, by the way, I will still hold office hours in the same time, all right, as before. So Monday, Thursday, if you want to meet with me any other time, let me know. Yeah, so the curve, I aim to get the passing grade for this class at 50%. Passing means a C, okay? That will, of course, push up the other, you know, B, A cutoff, that kind of thing, but not too far away from before, right? It go, but so what I'm saying is I said 40% was a C, right, in the midterm. Now try to aim at 50% for a C, all right? For a C. So for B, probably something like, you know, 70% or something, all right, 75, 80 something percent. If you worry about passing the course, even though, say, for example, that your total score do not make it to 50%, you can pass by doing okay on the final exam. In other words, if your performance on the final exam is at the class average, again, right, reflected by the statistics, the mean or the median, or, you know, you can get like 60% on the final or better, then you get a pass regardless of how you did before, you know, in the class so far. All right. So I'll put all of these, what I'm saying, in writing, so it's clear, right, and it's formal in the announcement coming up. Right. So basically, right, things will be slightly tougher on the final in terms of curve, not significantly tougher, but, you know, just make things more reasonable. You will still get a chance to pass if you do well on the final, right? Without worrying about what you did before. And again, right, if you have any questions, feel free to send me an email. I'll address your concerns. Otherwise, thank you for joining the semester, guys, and have a good summer if I don't get to see you. Okay. Yeah, thank you. You too. Thank you. You too.